Hey guys, this is the second part of the notes for evaluating functions and sequences. So we're going to go ahead and begin the sequences section of the notes. We have two types of sequences that we talk about in Algebra 1, which are arithmetic sequences and geometric sequences. So again, that's arithmetic sequence and geometric sequence. So these two sequences are fancy names for stuff that you've seen probably since elementary school. I think sequences are a pretty easy concept, but they just look super complicated for no reason. So I'll go ahead and give you some vocab and explain what this stuff means. So if we have an arithmetic sequence, this is a sequence. Oh, let me make my handwriting a little bit nicer. This is a sequence whose change is noted by addition or subtraction. So a sequence whose change is noted by addition or subtraction. So I'll give you a couple examples to kind of think through what that means. So an example here. First example is 1, 2, 3, 4. And so on and so forth. So a sequence is a list of numbers or an occurrence of numbers where there is a pattern that is happening. And with an arithmetic sequence, the change is addition or subtraction. So in this first example, you have 1, 2, 3, and 4. How is this changing? What is it doing each time? Well, it's adding 1 each time to get to the next term in the sequence. Another example of this could be 7, 9, 11, 13. What is it doing this time? I'm adding by 2. But just for the sake of change, we'll go ahead and add something where put down something, a sequence that's maybe subtracting. So this one, for example. What's happening in this sequence? 13, 10, 7, 4. It's subtracting 3 each time. 13 minus 3 is 10. 10 minus 3 is 7. 7 minus 3 is 4. So those are two sequences that are arithmetic sequences. Geometric sequences are sequences where the sequence whose change is noted by multiplication only. So only means only multiplication. There is no multiplication or division. So arithmetic sequences are addition or subtraction, whereas geometric is multiplication only. So there is no dividing sequence. There is no division type of sequence. So I'm going to go ahead and fix this really quick because this is bothering me. Change that, and I also need to change the U because it's also bothering me. All right, so I'll give you a couple examples of geometric sequences. So an example here would be 2, 4, 8, 16. So in this sequence, it kind of looks like it's addition at first. So 2 to 4 looks like it's maybe adding 2, but then you see 4 to 8. So this would be a geometric sequence because to get to the next term after the other, you are multiplying by 2. Another example could possibly be a negative number that you're multiplying by. So let's say we have 3, then negative 6, then positive 12, then negative 24. How am I getting all these numbers? Well, I'm taking the number and multiplying it by negative 2. 3 times negative 2 is negative 6. Negative 6 times negative 2 is positive 12 because a negative times a negative is a positive. And then 12 times negative 2 is negative 24. So you can multiply by negative numbers as well. All right, so then what does common difference and common ratio mean? So common difference and common ratio is a fancy word for something that's actually pretty simple. So let's go ahead and define it first. So common differences are related to arithmetic sequences. So if I have a common difference, that is the number. Sorry, I'm like way too far zoomed out for this. That is the number that is being added or subtracted in the sequence. Oops. Okay, so that's just a fancy way of saying that's the number that we're adding or subtracting. That's pretty much what that is. So with an arithmetic sequence, that has a relationship with a common difference. So if you have an arithmetic sequence, you automatically have a common difference. So for example, in that first example, 1, 2, 3, 4, your common difference is positive 1 because you're adding 1 each time. For the second example, 13, 10, 7, 4, your common difference is -3 because you are subtracting 3 each time. So it's just a fancy way of saying, oh, that's the number that I'm multiplying, or not, the fancy way of saying that's the number that I'm adding or subtracting by. And again, it's dependent on the sequence, so you could be adding something or you could be subtracting something. Now, if I have a common ratio, that is directly related to a geometric sequence. So if I have a geometric sequence, I automatically have a common ratio. A common ratio is the number that is being multiplied in the sequence. Whoops. So my common ratio for that second example in the geometric sequence would be +2 because I'm multiplying by +2 each time. My common ratio in the second geometric sequence is -2 because I'm multiplying by -2 each time. All right, so let's talk about the recursive form, or also known as the recursive rule. So this could be either way. So just to let you know that you could also see it say recursive rule. Oops, recursive rule. Also known as the same thing there, and I just hit backspace way too many times, so it took off the E. All right, so recursive form and recursive rule mean the same thing. So what does that mean? This is a formula that will help you generate terms in the sequence based on the previous term. So for example, if I gave you a formula and I said, hey, I want to find the 100th term. Well, I can't find the 100th term until I find the first 99, right? So if I say, okay, here's the pattern of my numbers. I have 2, 4, 8, 16. This first pattern here, 2, 4, 8, 16. And then these are the first 4 terms of the pattern. They said find the 27th one. Well, how am I supposed to find the 27th one? Well, I can only find the 27th one if I find the first 26. So these formulas help generate those numbers. So let's talk about the two formulas. So arithmetic and geometric formulas look identical to each other. They're pretty much the same thing, except there is one key difference. In an arithmetic sequence, the difference is you have plus d. Something is being added / subtracted, so you could add a negative number. That would mean you're subtracting. So you could see +4, +7, -3. So adding or subtracting is going to be arithmetic, and that's when you have a plus or a minus a number in the back. Now the formula has a plus because you can always add a negative, which would mean you're subtracting. A geometric sequence, the formula is exactly the same as an arithmetic, except that you have a multiplying a number, multiplying by r. Now the d and the r do stand for something. Like I said earlier, arithmetic sequences, if it is an arithmetic sequence, it automatically has a common difference. The common difference is your number you're adding or subtracting. So this d stands for common difference. Oops, I just spelled difference wrong. And this r value stands for common ratio. Now these two things are going to change depending on the problem that you have, right? Some problems you're adding 7, some problems you're multiplying by 3. So it's just dependent on what's happening. But everything else about this formula is pretty much going to stay the same. So let's go ahead and dissect what these formulas mean. So a of 1. So we talk about function notation in the first set of notes. So like f of x, we would pronounce it as f of x. So this is pronounced a of 1. Well, a of 1 is basically the first term. Why the first term? Because it's a of 1. It's telling us this is the first term of the entire sequence. This is the first thing that we need in order to get the entire sequence running. So for example, on the side, if I'm given a of 3, that's going to be the third term of the sequence. If I'm given a of 7, that's the 7th term. Oops. 7th term of the sequence. Now, it doesn't have to use a. Typically, they use a in most formulas, but you could use an f, like f of x. So if they said f of 4, they want you to find the 4th term of the sequence. So just keep in mind that they could use different letters as well. All right, now after we talk about a of 1, what else does the rest mean? Well, the a of n in the front means that this could be any term. So this is any term that you're looking for. So if I want to look for the 17th term, then I'm going to look for the 17th term, but I got to use this formula to generate the 17th term. All right, and then the next part of this, actually I'm going to use something other than red because I'm using red for something else, is the a of n minus 1. So a of n can be any term we're searching for. A of n minus 1 is the previous term. So like I said earlier, If I want to find the 27th number in my entire sequence, I got to find the first 26. So this formula says take the previous term, do something to it to get that term that you want. And I'll kind of show you what that looks like on the next page as well. Now again, this formula is exactly the same as arithmetic for the geometric side here. You have a of 1. Well again, a of 1 means that's the first term because it's a 1 in the inside. If it was a of 7, it'd be the 7th term. A of 5 would be the 5th term. The a of n at the front also means any term that you want to find here in that sequence. And then a of n minus 1 means this is the previous term. Oh my gosh, my t's keep looking funny. So that's going to be your previous term there. All right, so again, look at those formulas, exactly the same. It's just one extra number that you're going to see added in or multiplied in that will tell you what's happening in that rule. All right, so the first thing we're going to do is kind of get comfortable with determining whether some things are sequences or not and what kind of sequences they are. So, are the following sequences arithmetic or geometric? Remember, arithmetic sequences are sequences where you are adding or subtracting a number from term to term. So if I'm seeing that, oh, it's adding something, or if I see it's subtracting something, that's when I know it's arithmetic. Or if it's geometric, which means I have a multiplication pattern, go ahead and write that down. It's a multiplying pattern, then we would say it's geometric, and then we would say what the common ratio is. Now, after we decide whether it's arithmetic or geometric, we need to decide does it have a common ratio or does it have a common difference, and identify what that would be. Remember that a common difference is related to an arithmetic sequence. Arithmetic sequences have common differences. If you have a geometric sequence, you have a common ratio. So we'll start with number 1, 2, 4, 6, 8. So we're going to find a pattern that is happening here. So it looks like the pattern here is it's adding by 2 each time. Plus 2, 4 plus 2 is going to be 6, 6 plus 2 is going to be 8. Now for a sequence to be a sequence, the pattern has to stay the same the entire time. So we notice that it's adding 2 every single time, which means this is a sequence. This is an addition sequence, which means automatically we have an arithmetic sequence. Okay, we know that this is arithmetic because it's adding something. Once we figure out what that sequence is, we need to find the common difference / ratio. Because this is an arithmetic sequence, we're automatically going to have a common difference here. Well, our common difference is whatever number we are adding or subtracting, which in this case is positive 2. All right, moving on to number 2, we have 5, 10, 15, 20. So again, you're searching for a pattern here in the numbers if there is one. So you can kind of see, okay, did I multiply by 2? Did I add by 5? So you kind of look at the other numbers to kind of see what that pattern is. So it's looking that it's adding by 5 each time. So 5 plus 5 is 10, 10 plus 5 is 15, 15 plus 5 is 20. So this is also an arithmetic sequence. So I'm going to go ahead and say that it's arithmetic because it's adding a number here. And because it is arithmetic, it has a common difference. And we're going to identify what that is. And your common I spelled that wrong. Common difference here is going to be positive 5. Now you don't just need to say 5 or plus 5, or sorry, you don't need to say plus 5 here. If you just write a 5, I know it's a positive. Sorry, I'm struggling quite a bit with this 5. All right, let's move on to number 3. Negative 1, 1, negative 1, 1. Well, what's happening here? Well, the ones are kind of flip-flopping back and forth. So also notice how your signs are also flip-flopping. It's going negative, positive, negative, positive. Anytime that's happening, it means it's multiplying by a negative number. So we're multiplying by a negative number here. The problem is, or the question is, what number? It's multiplying by negative 1. Negative 1 times negative 1 is going to give me positive 1. And then 1 times negative 1 is negative 1. And then negative 1 times negative 1 is going to give me positive 1. So it's just multiplying by negative 1 over and over and over again. So just keep that in mind. If you see signs flip-flopping around, it means that you're multiplying by a negative number. So if we're multiplying here, then this is automatically a geometric sequence. And if it is a geometric sequence, then we have a common ratio. And remember, the common ratio is whatever number you are multiplying by. In this case, we are multiplying by negative 1. Moving on to number 4, we have 20, 10, 5, and then 2.5. So it looks like it's kind of dividing by 2, right? 20 divided by 2 is 10, 10 divided by 2 is 5, 5 divided by 2 is 2.5. The problem is that there are no sequences where we talk about division, but there are sequences where we can multiply, add, and subtract. So we got to figure out how we can make this in a way where, like, how can we say that it's doing something else and not division? So we are recognizing that, yes, it is dividing by 2. But what's the same thing as dividing by 2? Multiplying by a half. So I'm going to go ahead and kind of remind you that multiplying by a half is the same thing as dividing by 2. We talk about this when we do, like, when I ask you for, like, 100 times a half, right? So 1 over 2. It's half of that number, which is 50. So remember, 100 divided by 2 would still give me 50. So multiplying by a half is the same thing as dividing by 2. So this is essentially, multiplying by a half is the same thing as dividing by 2. So I'll go ahead and write that down, just kind of let you know that it's the same thing. So because it is multiplying in this case, we have a geometric sequence. And because we have a geometric sequence, we have a common ratio for this problem. And that common ratio is whatever number we are multiplying by, which is going to be 1/2. Now just a sidebar note, some examples. If I am dividing by 3, that really means I am multiplying by 1/3. Just like how if you're dividing by 2, you are multiplying by 1/2. It's the same exact thing. If I'm dividing by 5, I am multiplying by a 1/5. If I'm dividing by 9, I am multiplying by 1/9. So those are all the exact same thing. So if you're noticing a division pattern, it's not really division, it's a multiplication pattern, but you're multiplying fractions into it. So just make sure that you're aware of how to make that into a fraction. All right. So next we're going to be given some sequences, or some, not sequences, some formulas, some recursive rules, and we're asked to determine some terms here. So if a of 1 equals 7, and the recursive formula is a of n equals a of n minus 1 plus 4, find the next 3 terms. All right, so let's kind of dissect what's happening here. So the first thing that we see is a of 1 equals 7. So what does that even mean? Well, remember on the page before, a of 1 means the first term. So they're telling us that the first term is 7. So that's pretty important. And then they're giving us this recursive rule, this recursive formula. Now remember, I told you all formulas are the same except for one part. You'll notice something being added or subtracted or being multiplied. So look for that special number. In this case, that special number is right here, this positive 4. This positive 4 is going to tell me I am adding 4 to my sequence each time. Now I do want to let you know that you might see this in a different way. You might see the formula like this. So what's the difference between that formula and this formula? Nothing really. You're still adding 4 except the 4 is in the front. So the 4 doesn't necessarily have to be in the back. This still means that you're adding 4 even though it's in the front. So just be aware that the order doesn't matter. But we're looking for that number to tell us what we're doing here. So we're going to go ahead and acknowledge that, yes, we are adding 4 each time because it says plus 4. The big goal here is to find the next 3 terms. So we want to pay attention to what we're asked to find here, which is the next 3. Not the first 3, but the next 3. So we are given the first term. The first term we are given is 7. A of 1 is 7. So if that's my first term, that's pretty important to know. So I'll go ahead and kind of do some blanks here. So 7 is my first term. And they want me to find the next 3 terms in the sequence. So the next one is the second, the third, and the fourth term. So I need to find the second, the third, and the fourth term here. Well, how do I do that? I'm going to use that formula to help me do that. The formula says I'm going to add 4 to my first term to get the next 3 terms. So my first term is 7. I'm going to add 4 to that, and I get 11. Well, how do I get the next term? I'm going to take the previous term, which was 11, and add 4 to that, which is 15. I'm going to take 15, which is the previous term, to get the next term and get 19. Now, the big question here was find the next 3 terms. And I did find the next 3 terms. It was 11, 15, and 19. But we want to write that in function notation. So the function here, they're using a's, so we're going to go ahead and use a's. So the next 3 terms, we already found the first one. We don't need to say that a of 1 is 7. We already know that. So they want the next 3. So they want the second term, which is a of 2. They want the third term, which is a of 15. And they want the fourth term, which is a of 19. So we're going to go ahead and write a of 2 is 11, a of 3 is 15, and a of 4 is 19. So we found the next 3 terms. Now, why is this formula useful and why is it even there, right? So here's how the formula is actually used. So I'm going to go ahead and show you that. They told me that the first term is 7, and then they tell me the formula is this right here. Well, on the previous page, this stuff right here meant the previous term. So in a sequence, of a recursive sequence. To find the next term, I need the previous term. So a of 2 means I want to find the second term, because a of 1 means the first, sorry, my iPad is starting to like freeze on my app. All right, a of 1 is 7, a of 2 means I want to find the second term. Well, how do I find it? I got to use the previous term. So I'll show you how to do that. So I'm going to go ahead, I'm saying that I want to find the second term, so a of 2. So anywhere I see a 2 here, I'm going to plug in, or anywhere I see an n, I'm going to plug in a 2, because n is the term number I'm looking for. So I claim, hey, I want to find the second term. We're going to find the second term by plugging in a 2 anywhere I see an n, because that's the number I'm looking for. So let's go ahead and simplify this down. Well, that would be a of 1, because 2 minus 1 is 1. And then I have this left. And then I have to figure out what the heck does a of 1 mean. Well, didn't they tell us what a of 1 equals? They said a of 1 equals 7. So that's really 7 plus 4. Well, what's 7 plus 4? That's 11. And that's how it gets that second term. You're like, wow, why would you do all that math to do that? Typically, we don't always use all this stuff to do the pattern, because it seems like a pretty obvious pattern to do, so we can do most of it in our head, but that's how the function is used. That's how you find the second, the third, and the fourth. Now, it's asking to find the next 3. Careful, right? Because it didn't ask us to find the first 3, because if it asked to find the first 3, we would have a of 1, a of 2, and a of 3. But because it wants the next 3, and they already gave us the first one, then we would find the second, the third, and the fourth. So 2, 3, and 4 there. All right. So if a of 1 equals 3, and the recursive formula is a of n equals a of n minus 1 times negative 2, find the fourth term. All right, so let's dissect this a little bit. We are given the a of 1 equals 3 here. No, a of 1 is our first term, so I'm going to go ahead and dissect that there and be like, okay, that's the first number. So in our sequence, in our pattern, 3 is the first number in that sequence. All right, then they give us the recursive rule or formula here. And again, all formulas look all the same, except we are given a number in there that tells us what's happening in here. And in this case, it's telling us we're multiplying by negative 2. Notice that dot there means we're multiplying. Now again, this could have also been written like this, so just keep that in mind, that this means the exact same thing. And you're like, I don't see the multiplication symbol. Remember, in math, we don't have to put a multiplication symbol to say that it's multiplying, right? So negative 2 times a of n minus 1. Oh wait, I forgot the equal sign. There we go. So that also means the exact same thing. So just be very mindful of how things can look differently and how it can mean the exact same thing at the same time. This problem wants us to find the fourth term. So we don't care about the first term or the second term or the third term. We want to find the fourth term here. Now we still need to find the first, second, and third to get to the fourth term, but we want the fourth term as our final answer. So let's go ahead and write our pattern here. The first term in this pattern is 3. Now we want to find the fourth term. So 3 is the first, so we have to find the second, the third, and then we can find the fourth term. And that fourth term is going to be our answer and what we actually want to find here. So let's go ahead and use this pattern to our advantage. In this pattern, it's saying we're going to multiply by negative 2. So what is 3 times negative 2? That's going to be negative 6. And then how do I get the next term? I'm going to multiply again by negative 2. So negative 2 is a number I am multiplying by to keep getting my sequence going in my terms. So negative 6 times negative 2 is positive 12. And then positive 12 times negative 2 is going to be negative 24. So my final answer is going to be negative 24. Oops. But I want to write this in function notation. So it wants us to find the fourth term. So the fourth term is going to be noted by a of 4. So a of 4, that's a little too small, I think. A of 4, in this case, our fourth term is negative 24. So I found the fourth term, and I want to make sure that I let the reader know, hey, I found it. This is the fourth term. All right, just like how we did it in this last problem here. All right, given the sequence 20, 15, 10, 5, write the recursive definition. So writing the recursive definition is the same thing as writing the recursive rule, writing the recursive formula. We're writing the sequence, the formula here. So we're given the sequence 20, 15, 10, and 5. We're going to write the recursive definition. So to find or write the recursive definition, we want to state two things. We want to state the first term, and we want to state the pattern that's happening. So essentially what we're doing is we're making one of our own formulas. So the first thing we want to do is find the first term. So finding the first term here is, well, the first term is 20. So I'm going to go ahead and write a of 1 equals 20. That's my first term. Now again, the backbone of all formulas, I'll go ahead and write it on the side. So a of 1 equals the first term, and then you have a of n equals a of n minus 1, and then there's something in the back here, right? So that's the backbone of every problem. It could be plus a number, it could be times a number, it could be subtracting a number, so just kind of letting you know what they all look like. So a of 1 equals 20, and then the rest of the formula is a of n equals a of n minus 1, because again, they all look the same, because if you haven't noticed, they all start with a of n equals a of n minus 1, a of n equals n minus 1, a of n equals n minus 1, right? So they're all the same start. So I have that as my starting, and I'll go ahead and put that in black ink to let you know that that's going to stay the same. The 20 is our first term, so that's why we write 20 for a of 1. And then let's figure out the pattern that's happening here. So 20 to 5, 5 to 10, 10 to 5. So it looks like it's subtracting 5 each time to get to the next term. So in our sequence here, we're going to say that it is subtracting 5. And that would be our final answer. All it wanted us to do was to create the formula that would make this pattern, and that's the pattern there. That's the formula. Now we're given the sequence 1, -3, 9, -27. Write the recursive definition. Again, we're writing that formula. So the first thing I want to do is I want to find that first term so I can help the person who is using the formula know where to start. So our first term in this case is going to be this +1. Remember, it's whatever you see first in that sequence. So a of 1 is a of 1 is going to be 1 here, our first term. And then we're going to go ahead and write down the recursive definition, or the recursive formula here. So a of n equals a of n minus 1. And then we need to figure out how is this pattern changing. So we have 1 to -3, -3 to 9, 9 to -27. So what is the pattern that is happening here? We are multiplying by -3. So 1 times -3 is -3. -3 times -3 is +9. And +9 times -3 is -27. So we are multiplying by -3 here, which is our pattern. Now, I am going to write the formula another way to let you know that there is technically another way to write this formula. So I'm going to go ahead and put or over here. We could have a of 1 equals 1, like we did earlier. And then we have a of n equals, but instead of having the -3 in the back, we could also have it in the front. And then it could be a of n minus 1. Now, again, they don't have to use a. So remember when we were doing functions on the previous section, right? These functions were h of x, g of x, g of n, h of n, p of t. So you don't have to use a's when you're doing sequences, but it's the most commonly used thing. But if you see another letter, just recognize it means the exact same thing as well. So this, with the -3 in the front, I already know it's being multiplied, so this means the exact same thing as what I have on that left-hand side. But yeah, that's it for sequences. So you have two types, arithmetic and geometric. And just remember, when you have a arithmetic sequence, you have a common ratio. So back here, when we notice that, hey, it's subtracting by 5 each time, -5 or -5 is your common ratio because that's what you're adding or subtracting by. And when you have a geometric sequence like this one where you're multiplying, you're going to have a common ratio. So your common ratio for this last one is -3.